Hello, and welcome to the, I believe, sixth lecture in the 10-part series that we are working on. Today we're going to cover a little bit more application and maybe some other stuff regarding my processes and how we can get to the bottom of our revamping of math and our revolution of math and how we're changing math and thereby changing the world as we know it. Don't be scared. I'm just kidding. So, where we left off, I believe, was we already talked about the duality of the side approaching infinite paradigm in the definition of a circle's number of sides. We branched into number theory slightly, recognizing that 1, 3, and 4 were important numbers. Let's footnote that. We said that we're changing geometry. Fine. We said that, I don't know if I mentioned a polygon. Oh, I tried to search for the word polyhedron when I was describing a crystal. It's polyhedron. But a polygon in two-dimensional geometry, which I believe means it's Euclidean, but I cannot remember, and that's not important. Sorry, Euclid. But where was I? So a polygon, the only important shape of a polygon is a square, and I cannot, or a rectangle, because I cannot emphasize how little importance the number 5 and so on is in geometry. You don't need anything above a 4. So, because for example, a pentagon is not even an important shape because it can be broken down into, I guess, two square and two equal congruent triangles or something. But let's just focus that 4 is the max. Anyway, we had our revelations or extensions in number theory, and then we got a little bit into physics actually at the end, because I think that's where this is headed. So I'm still scared to think of a reawakening in nuclear physics or energy physics. I don't even know if it would be nuclear physics. Maybe we've done all we can with the atom or the nucleus. Thank you, Einstein, but I know light is involved. But anyway, getting back to the polyhedron, and we have a light getting a ray of light, photons or something. Let's call it a ray getting trapped inside of a polyhedron or a crystal. What happens to that ray of light? It's essentially approaching, in math, we would say it's approaching an asymptote continually or continuously. We're talking a ray of light continuously getting trapped inside a shifting side, or in math, the synonym would be an asymptote, a vertical asymptote on the x-axis. So that's what we're talking about. We're talking about asymptotic, shifting asymptotes. How is this relevant? So that's what we got to figure out, right? So, and this discussion is going crazy. We're getting through math, and it started off as a revamping of math, and clearly we're getting into physics now. So I should probably bring it back to math. But it's an interesting aside that these physics applications could be, and this is called stream of thought. So we're getting into how the asymptote is an important idea in this whole theorem, which started off as just explaining a circle as having exactly 2 sides, and that property was 0 and approaching infinite. But, we have 4 more lectures, I think, so after this one. I'm not sure what I did want to talk about more so on that subject. Number theory would be interesting. Is number theory more primitive and basic than geometry? I have a feeling it might be, or not. It could just be more abstract. Because when you think about cavemen or cave people or whatever, early people, the Homo sapiens, let's call them, the early people who there was rhythm, clearly the drum rhythm, and then there was clearly jotting stuff on walls. And once you pick up something and you do a line on a wall, that could be considered geometry, really, because what is geometry besides a bunch of lines? I think about it. Even if it's art can be mathematical. It can be. So I mean, look at Godel, Escher, Bach, the book, but and I forget who that's by, but for sure we have geometry being an extremely early branch in math, like extremely early, one of the earliest, but maybe in my opinion, possibly, or in my thought, possibly the second earliest branch after music. And music theory is essentially rooted in math. It is very mathematical, um, extraordinarily mathematical. And four, by the way, is a clue because in math and music, sorry, a lot of stuff is four. Come on, except we're not talking a waltz or something. We got 1, 2, 3, 4, and then we have the divisional fours, the quarter notes, eighth notes, 16th notes, 32nd notes, 64th notes, 128th notes, 300 and blah 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 notes. 354. Yeah, 356th note would be the next one, I guess. So after that, 356th, and then 7, right, 8, 7, 12th, 1, 7, 12th. No, anyway, we keep going, something like that. But 4 is such an important number in music. It's so important that we cannot ignore it in literally any other branch of math going after that, whether it's trig, whether it's geo, whether it's geometry, whether it's calculus, anything math related after music. 4 is a number that must be actually seriously taken under the microscope and looked at. But I consider it a limit in number theory, like something higher. It just so happens pi is lower than 4, which will, pi is a crazy number. Pi is an insane number. Like pi is insane. But anyway, suffice it to say, I like 4. And I forget where we're going with this again, but so revolution in math, revamping math. Let's focus on the math, the pure math of it. So what else do we want to talk about? So we had an observation, then we had, do we have a theorem yet? Because there needs to be a theorem, and then there needs to be an attempt at proving that theorem, and that attempt could be left to others. And you know, there should be a formal theorem written out at some point, and you know, or not actually. Did Einstein have theories or theorems? Theory of relativity. You know, I don't know where this is going at all. There should be a theorem. There should be a theorem. I don't think a theorem would be a circle has 2 sides exactly. That's kind of simple. Maybe it would be a theorem. Prove that a circle has 2 sides. Prove that a circle has 2 sides would be the theorem, I suppose. A circle has 2 sides. A circle has no more than 2 sides. No, a circle has exactly 2 sides. And then from there, proof would require some kind of diagram, perhaps, or getting into the undetermined ratio. But a circle, let's just say the theorem could be a circle has 2 sides. A circle has the shape circle, a circle has 2 sides could be a theorem. A circle has 2 sides. But and again, like, I mean, is that obvious? Is that something that people would immediately snap back with? Of course it has 2 sides, 0 and approaching infinite, or 0 and infinite. But so, I mean, maybe it's not even that revolutionary. Maybe it's not a theorem. Maybe I'm just talking into the wind. Maybe it's an observation. Maybe I'm not a mathematician. But we can start there. We can even develop subsequent theories or theorems based on that observation. In science, we always have, and maybe I'm more of a scientist than anything else now that I think about it, but a mad scientist. But math is cool. And then we have, no, I like math more than science for sure. But, you know, I mean, like, there has to be some kind of theorem that we can pull out of this observation, the side duality. That is 10 minutes, and I have talked a lot, and I need a coffee or something. So I'm going to sign off and say goodbye. Tune in tomorrow for the 7th lecture in the 10 lecture series. 100% free, obviously, and always will be on YouTube. But check it out. Okay, bye.